Hey everybody, this is our continuation about talking about antibiotics, and particularly the penicillins and the cephalosporin classes of antibiotics. This is benzoyl penicillin, and this is an example of a cephalosporin. And I stopped kind of midway through this just because I was running out of time. Just want to continue discussing these two molecules and sort of the very simple synthesis procedure that can be used. Yeah, so we talked about benzoyl penicillin, and what's cool about these is that you can basically build it from a single step from a very widely available molecule called 6-APA, or 6-amino penicillinic acid, which is 50 grams for $140, so relatively cheap. And like in this example, we're reacting an amine with an acid chloride to make the amide linkage, right? And we talked about EDCI and like peptide coupling reactions or amide coupling reactions, and those can be used also. We'll show that just for an example in a few minutes. Also, we mentioned that you don't really need a protecting group. If you have an amine and a carboxylic acid, and you're reacting with something that already has a leaving group on it, like this acid chloride, a protecting group doesn't hurt, but you can often get away with no protecting group at all, and they're successfully doing this without a protecting group on here, and that's because that's reactive and that's reactive, and they form the amide, and that's not really involved. Okay, what other little tidbits here? Yeah, what's the name of this mechanism? And remember, our kind of theme right now is carbonyls, and this is just another carbonyl reaction. So I like to abbreviate it NAS, which is nucleophilic acyl substitution. Nucleophilic acyl substitution. And I think that's in the Volhard book, was chapter I think it's 19 and 20. I think that's right. Okay. And what is the mechanism of that? Another thing they call it is addition elimination, but the basic idea is like this nitrogen. Well, so the base is involved, right? The base is involved, but the base is not involved initially. The base actually, what happens is this is highly nucleophilic. It attacks, and then the base comes and takes that proton off. Okay? So it's not like the base takes the proton off now, because it's actually very non-acidic. It's actually kind of a two-step process. Nucleophilic attack, then the base comes, takes off the proton, and then it all falls apart, and you make the amide. But for the goal of brevity, I just abbreviate this as attack. Electrons go up. Technically, that's probably now when the base takes off that proton, because the proton becomes highly acidic. But we're kind of abbreviating. So yeah, attack, and then the electrons go onto the oxygen. Sometimes it's up, but here it's down, and then it goes back up and kicks out the chlorine. Okay, so this is a very abbreviated mechanism, and you know, if you're taking organic 2, I would say no, you can't. You got to draw it all out, but we're not showing every little detail here. Okay, cool. So what else about these? Yeah, then we started talking about cephalosporin. This is a cephalosporin antibiotic, and you know that from the 6-member ring here, 6, and the alkene and the double bond. There's this acetate over here also. This was actually the first cephalosporin ever marketed. I think in 1964. is when it started, and it's still used today. There's a lot of other fancy cephalosporins also, and we'll show a couple more of them. Okay, so if we just consider the synthesis of it, I gave you a hint that maybe we can just build that amide linkage right there, also from a dirt cheap building block. And yeah, that's exactly what we're going to do. So I can just kind of imagine redrawing this, but with that as an acid chloride. Just draw that as an acid chloride with the leaving group on it, and then draw this as basically just the amine, and that is the 7-ACA. Okay, so oh yeah, and what was this thing called? This little funny thing is a thiophene. Thiophene. It's a heterocycle. It's one of the that is heterocycle, so it's a ring with a heteroatom like sulfur. That's a very common one. Thiophene has got CH2, and then basically we'll draw an acid chloride. Okay. All right. Okay, so there we are, and you can see the CH2 right there. Okay, so yeah, that's the electrophile, the thing that's going to get attacked, and then the nucleophile is going to be sort of the right side of this. So, and that's what the 7-ACA is. Okay, so it's H2N. Don't forget the sulfur. And then we have carboxylic acid off the alkene, and a CHO acetate hanging off the ring like that, and then the stereochemistry is coming toward us. Okay, good. So this thing, I mean, it's the same exact mechanism. You would need a base in there, usually triethylamine or pyridine or something. But the mechanism is also that, you know, nitrogen attacks, probably then the base takes the proton, but we're skipping that detail. Up, down, off. Up, down, off. And what's the 3-letter abbreviation for that mechanism? NAS. Which is nucleophilic acyl substitution. Okay, cool. So that's 7-ACA. You might ask, if this is kind of cheap, do you think this is kind of cheap? And yes, the answer is yes. Very cheap. 25 grams for $100. So, comparatively, about the same. Maybe this is a little bit more expensive, but I guess the point is that we can make cephalosporin antibiotics very inexpensively. Okay, all right. Okay, so numbering systems back to number 6 reactions. Carbonyl, enol, aldol. And we're on E, the beta-lactam antibiotics. Before we continue, just a couple quick notes about these things. And we'll talk about the mechanism of them in a bit also. But those 6-APA starting material and 7-ACA, the starting materials are super versatile. meaning, you know, you can use them as these nice building blocks just to make all sorts of derivatives. And of course, antibiotics are a popular drug type because of the, you know, the prevalence of bacterial infections, which is pretty crazy, and also drug-resistant infections. So super versatile, and somewhere I read that the people have made about 50,000 analogs just using those building blocks, 50,000 derivatives. And you know, not a handful of them are actually used commercially, but it's nice that it's so easy. It could even be a student project. Just take 6-APA and react it with some different acid chlorides or whatever, or 7-ACA, and do the same. And you can just build like libraries of molecules. So other note, the penicillins in general, penicillins are usually used for gram-positive bacteria. And while the cephalosporins are maybe more widely used for, or more effective against gram-negative bacteria. Which one was the more complicated one, maybe? In terms of the cell wall, the gram-negative have that outer cell wall, and so sometimes it's a little more tricky to get through that. So, you know, depending on the bacteria type, you might use a penicillin or a cephalosporin to treat it. But we will see an example of a penicillin that actually does work for gram-negative. I think it's ampicillin, and it kind of sneaks through the porin, which is the little pore in the cell wall. Okay. Oh yeah, and then we can just say, you know, some antibiotics are broad spectrum. Which would mean they just are effective against all kinds of bacteria. And of course, you wouldn't necessarily use a broad spectrum antibiotic for everything, otherwise drug resistance becomes more of a problem. But yeah, some of the antibiotics will work against gram-positive and gram-negative bacteria. And then we'll talk about the mechanism a little bit. Both interfere with the synthesis of that thing called the peptidoglycan. Which is, you know, it's basically the cell wall in the gram-positive bacteria, and then it's kind of like an inner cell wall in the gram-negative bacteria. It's the purple kind of wall thing that I showed in my figure before. And of course, I mean, if you're trying to kill bacteria, you know, breaking apart or preventing the synthesis of its wall will totally do that. Okay, so we'll come back to that in a little bit. All right. So what else? That's it for this slide. Let's show an example of a couple penicillin derivatives and how they're easily synthesized. So one of them is methicillin, which is a very common penicillin derivative even today. So it's just really going to be a matter of using the proper carboxylic acid or acid chloride type thing, and then that stuff 6-APA, and that just kind of comes together. In this example, though, I'm going to use this carboxylic acid. The benzoic acid with 2 methoxy groups, and rather than acid chloride, but we're going to react it with H2N, the 6-APA. And we're going to, and I'm actually ignoring stereochemistry now just to make this a little easier. So this is 6-APA, but we're using the methyl ester of it, which is also cheap and available. So it's the methyl ester of 6-APA. And the reason we're doing that is just because I want to highlight the use of those reactions we just learned. What were the cool reactions that just magically attach an amine and a carboxylic acid? Remember those? What's it called? Something coupling. You could say amide coupling or peptide coupling. This isn't exactly a peptide, but it's the same kind of concept. In order to do that, using those reactions, those reagents, we do actually need a protecting group, and that's why I use the methyl ester here. Okay, so yeah, we're using 6-APA methyl ester, this dirt cheap benzoic acid derivative. What was the reagent? We had a couple of them, right? We could use DCC or DIC, or we could use EDCI. All of those work. And what the reason you'd maybe use EDCI was it's just easier to remove. So generally speaking, everybody uses EDCI, and maybe not these guys. But we could also use, and we talked about these other ones, we could use like ET3N2 and then like HBTU. All of these are effective ways to make an amide bond. And I thought the kind of cool ones were EDCI and this other HBTU method. But essentially what happens is you form the amide. Okay. What else do we have to do? We have to remove the ester, and we can do that with just NaOH. Methanol or something like that. That's just ester hydrolysis. And then the end result is we get methicillin, which is popular penicillin derivative antibiotic. Alright, so we got our 2 methoxys. Oh, you know, I made a boo-boo. Back here is nitrogen. Right there at the bottom. Nitrogen. Okay, yeah, sorry about that. That's 6-APA is nitrogen. Of course, that's a beta-lactam. Without the nitrogen, it's not a lactam. So we have to do that over here too. Nitrogen. Okay. Okay, so there's methicillin. And I'm kind of ignoring stereochemistry, just draw these really easy now. Okay, and yeah, so these things, one of these things can be used to make the amide linkage, and then like NaOH is a standard ester hydrolysis of the methyl ester to the carboxylic acid. And this is methicillin. This is used, are these used usually for gram-positive or gram-negative? Well, the penicillin derivatives, which have the 5-member ring here, those are typically gram-positive. So, typically gram-positive. Bacteria. And some drug-resistant strains. Bacteria also are treated with methicillin. Okay, cool. Alright, another very popular clinically used penicillin derivative is ampicillin. A couple more steps to the synthesis, but it's really easy. And so they use phenylglycine, which is a non-natural amino acid, H2N. So is that natural or non-natural? Phenylglycine. Phenylglycine. You ever heard of that before? You ever seen any amino acids that kind of look like that? You might think of phenylalanine, which is the same thing, but there's like a carbon, then a CH2, and then a phenyl. So phenylalanine is a common natural amino acid. Phenylglycine is kind of a weird one that's not one of the standard amino acids that we find in proteins. But we're not using it for a protein. We're using it as part of our synthesis of ampicillin. Okay, so I'm just gonna abbreviate a little bit. They need to attach a protecting group on nitrogen, and I'm just gonna abbreviate that. I'll draw what it looks like in a bit, and I'll tell you about it briefly. It's called CBZ. It's a nice nitrogen protecting group. Yeah, I'm kind of ignoring stereochemistry for now, just to make this easier. Okay, so this CBZ is a nitrogen protecting group. And it'll come off, I'll show you, but it's like H2 takes it off. H2 gas, palladium. Alright, cool. So then, in this case, rather than using our nifty EDCI or coupling reaction, they actually convert it to an acid chloride. So they convert this whole thing to an acid chloride, and that's CBZ, nitrogen, there's a million ways to convert a carboxylic acid to an acid chloride. I'm really not going to talk about that, but I actually have ones I use in the lab that I like a lot that are very easy. The one you know from organic was SOCl2. In reality, though, not too many people use SOCl2 anymore, just because it's so stinky and kind of toxic and stuff. I can talk, if you ever want to know about cool ways to make acid chlorides, I can tell you. Anyway, yeah, so, and for penicillin derivatives, do they use 6-APA or 7-ACA? It was 6-APA. 6-APA, which was, I'll just abbreviate it, H2N, nitrogen, blah, blah, and CO2H. CO2H. Okay, so yeah, it's got that the beta-lactam, and there's a couple methyls and sulfur and stuff. But essentially now it's just that attacks, kicks off the chlorine. And not done yet though. You make CBZ, protected, nitrogen. Let's abbreviate the phenyl as pH for the phenylglycine. Yeah. Okay, so what do we have yet to do? We have to take off the protecting group. We have to take off the protecting group. And so then the question is, how do you take a CBZ group off? I will tell you, and then I'll explain kind of how it works in a minute or two. Okay, so it's H2, palladium on carbon, which is, well, that just happens to react nicely with the CBZ group in order to remove it. And we get the final product, ampicillin, H2N, Methyl. Okay. Draw the arrow differently here. Cool. Alright, so this is ampicillin. Which is a broad spectrum antibiotic. So it's effective against gram-positive and gram-negative. Sorry. Bacteria. And so, thinking about the structure of this, and maybe comparing it to ampicillin, which is just a different one of these things. What's the key difference? And you know, this is mostly just gram-positive bacteria. This actually sneaks through the cell wall of gram-negative bacteria. And how might it do that? What's kind of unique in the structure? You know, the other one had that kind of big benzene thing up here with the dimethoxybenzene. But this has something kind of unique, and that's the phenyl. Sorry, not the phenyl, the nitrogen, right? And so the nitrogen is, the nitrogen can get kind of protonated, right? Physiological pH. Protonated, so it turns into a kind of a polar type thing. And it is able to sneak through that thing called the porin we're talking about in the gram-negative bacteria. So this functional group basically helps it, turns it kind of into a semi-broad spectrum antibiotic that treats both types of illnesses, or both types of bacteria. Okay, so that's kind of cool. And other penicillins don't do this, so that's kind of why ampicillin, you know, it's used very commonly to treat infections. It's kind of a first course, pretty easy treatment. And often, like if you'd have maybe a cough or some sort of bacterial infection, this might be the first drug that they would prescribe to you at the doctor's office. Okay, let's talk about the CBZ thing just real quickly, just because it's so easy and kind of cool. So what is CBZ and how do you take it off? Alright, so CBZ, and I'm just going to draw a miscellaneous, yeah, I'm going to fit it up here just because I'll do it on the back of the page. Alright, here's CBZ. Let's talk about CBZ. Just got to figure out where to draw this. Alright, so CBZ, let's just draw a miscellaneous amine with CBZ on it. So CBZ is this thing, alright, CBZ. So CBZ is really this whole thing, not including the nitrogen. CBZ. Alright, so we could abbreviate this molecule NHCBZ. Alright, cool. So CBZ can be removed with what? We said it just a second ago. What's the magic way to take off a CBZ group? H2 palladium on carbon. So H2 means hydrogen, usually like a balloon of hydrogen. PDC basically means palladium absorbed onto carbon, and it's basically charcoal. It looks like charcoal. It's like a black powder. And then the byproducts are CO2 and toluene, which is methylbenzene, like that. Okay, so how does this all work? It's actually pretty easy. Alright, so going back to organic chemistry, you may or may not remember what happens when hydrogen sees palladium or metals. So essentially you got, there's the metal, it's a surface, hydrogen gets absorbed onto it, so I just draw hydrogen dot 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 dot. Something like this happens, and hydrogen gets absorbed onto the metal. What do we got now? We have hydrogen absorbed on the metal. So now what I'm going to do is I'm going to draw my CBZ, And the big thing I have to do is draw the oxygen and the CH2 and then the benzene. And then of course this stuff, which does not really matter. Okay, cool. So the CBZ group, and really it's just this benzoyl thing. Remember, that's called benzoyl. Phenyl CH2 benzoyl. The benzoyl group really just kind of lines up with the H2, and then essentially we have dot 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 dot, and the H2 essentially cleaves this bond. The way it does that is arrow, 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 and that regenerates the catalyst, which is palladium. So we get palladium out, palladium goes in, palladium goes out, and then we get this thing. We get, that's where, see where we got toluene from, CH3 benzene? Well, that's from there, because this thing basically just grabs a proton and it goes from CH2 to CH3. So that's how we get toluene. Toluene is methylbenzene here. Okay, so we get, that's where that came from. Alright, well, cool. And then how does this turn into amine plus CO2? Really easily. This kicks in, kicks this off, essentially. And that essentially makes CO2. You lose a proton. And you kind of move that proton from the oxygen to the nitrogen through this process. But that basically makes the nitrogen and CO2. Okay. Any other names of these things? Yeah, this CBZ group is called a carbamate protecting group. Carbamate, PG. Carbamate just refers to the nitrogen, the acetyl bond O, and the oxygen and carbon. So this whole thing is called a carbamate, and there's a whole bunch of carbamate protecting groups. This is just one of them. Something called BOC and FMOC, which are all variations of this. Okay, that's carbamate. You may or may not know what this is called from, I think I teach it in my Organic 2 class somewhere. But that's not a carbamate anymore. It looks almost like a carbamate with the acid on it, right? So it's called a carbamic acid. Okay, cool. So that explained, that was all kind of in the context of the ampicillin synthesis, alright? Cool. Alright, so we were kind of talking about the how these penicillin derivatives are prepared, very simply. Let's talk about some cephalosporins now, which are also prepared very simply. Cephalosporin, sporins. And these are maybe a little more useful in the gram-negative bacteria. So just a couple simple examples. Let me use. First one is Cephalosporin. Cephalosporin. Alright, so pyridine. Pyridine with a CH2 and acid chloride, and then we're using our kind of fancy cheap building block, 7-APA. Remember, the cephalosporins have a 6-member ring. They also have this acetate out here, the CH2 and then the acetate thing. Okay, so yeah, with you have the acid chloride, it's ready to go. We don't need to activate this or use a peptide coupling agent or anything like that. what do you need to throw in for a nitrogen to kick off the acid chloride? What kind of reagent do you add? Just a base. Triethylamine or pyridine or something like that. In the mechanism, 3 letters, NAS. As we've seen many times. Very common reaction. So yeah, mechanistically it's super easy. It's just attacks, and like I said, probably attacks, then the base comes in to take off one of the protons. And then, well, actually it attacks, electrons go up, and then the base takes the proton. And then this collapses, kicks off the chlorine, right? So nitrogen attacks, electrons go up, then the base takes the proton, then the O- swings down, regenerates the double bond, kicks off the chlorine, and that's basically NAS, right? So the final product is pretty simple. We should be able to draw this, right? You should be able to draw the product of this. It's these two things attached with the amide linkage. What did I call this thing? Nitrogen with the benzene, or aromatic heterocycle with the benzene, is pyridine. So this thing's got pyridine attached to it. Okay, pyridine. This, if you just consider this molecule by itself, that's called pyridine. It's very stinky, nasty chemical. Yeah. Okay. But we use that as a base, a mild base in organic chemistry. Nitrogen. Draw the H up there. Cool, and this is Cephalosporin. And as a cephalosporin, is it active against gram-positive or gram-negative or both? This is actually active against both. Gram-positive and gram-negative. What else about it? I think it's used in like respiratory infections. Ear infections, I think. A couple other types of bacterial infections. Okay, cool. One more, and this is cool because this next one is pretty cool because I mean, thinking about the structure, what are the key parts of this? Well, you got the pyridine, you got the cephalosporin part, and you have like this acetate. And in the next molecule, what we're going to show is you can kind of vary this part, and they did, and but they can also kind of vary this and sort of attach stuff to it. So that's pretty cool, and that allows you to kind of like, you can vary one thing, vary another thing, and then have more points of modification in the molecule, which I always find is cool for as a medicinal chemist, is being able to change two things. Because if you just consider this molecule, you'd probably assume, yeah, you know, you could play around with this and vary this and modify it to see what effect it has, but you probably keep the acetate there. In the next molecule, we'll see that they actually vary both of these things. Okay. What else to say about this? Anything else? I had something to say, but I forgot what I was going to say. All right, so let's do that next one. All right, so another cephalosporin. Oh yeah, I think I remember what I was going to say. I don't know if this is 100% true, but if you remember with ampicillin, the penicillin derivative that's gram positive and gram negative active, it had a nitrogen, like an NH2. Where's the structure? It's right here. Ampicillin had that polar functional group here, kind of on the left. It is interesting to note that they have a pyridine here, and the pyridine is actually kind of a polar heterocycle, and that may be part of the, that may contribute to it being active against gram-negative bacteria, because this can get protonated, or well, it's certainly a polar component of the molecule, and that may help it sneak through the porin. I'm not 100% sure about that, but I mean, we'll see. Like the next molecule also has a kind of a polar thing on the left side over here, so that may be what's going on. All right. Okay, so let's do this next one. One more. Cephalosporin. This one's called Cephalosporin. I think I had this on my cartoon diagram earlier. Kind of interesting structure. I like interesting structures. Cephalosporin. Alright, so we're going to use, rather than pyridine, which is a polar heterocycle, we're going to use a different polar heterocycle, which is, I'll draw it over here, nitrogen, double bond, nitrogen, double bond, and then nitrogen, single bond, and we'll just start with carboxylic acid. Okay, so have you ever seen that before? As a heterocycle, if you just ignore the this part, any guess what that might be called? Tetra something, and like in these heterocycles, when you have nitrogen, you usually call it zol, Z-O-L, like this is imidazole. Or have you heard of that molecule before? Imidazole, and if you have 3 nitrogens, it's called triazole. If I sneak another nitrogen in there, it's called triazole. So what do you think it's called if you have 4 nitrogens? Is it something zol, right? 4 nitrogens, not imidazole, which is 2, or triazole, which is 3. It's called tetrazole. So this little ring system is called tetrazole. It's found in a lot of drugs because it's it definitely is polar. It kind of enhances the aqueous solubility of the drug, so it does that. And you know, this may actually be important in the ultimate gram-negative activity of this, the final product. All right. Okay. So, all I'm going to do is really turn it into a chloride, then attach it to my 7-ACA, and then there's one more cool step. All right. So, SOCl2. What does that do? Again, in the real world, nobody uses SOCl2 really anymore, but this is what you guys learned in Organic 2. It turns the OH into a something. Five-member ring. Converts the OH into a chloride, right? So, yeah, and into a good leaving group. You could probably directly use the OH and the amine to make the amide, like all of these things, but you might need a protecting group. This, though, does work, and you make the acid chloride nicely. Okay, so then we got the acid chloride, and now we do our, I'm not gonna redraw 7-ACA again, we just saw it. Actually, right up here, let's write in 7-ACA. Okay, so if we assume 7-ACA, what do we get? Now you get the cephalosporin, but there will be one more cool step. Alright, so redraw my tetrazole. acetyl bond O, nitrogen, there's my beta-lactam, and then the cephalosporins have the 6-member ring. And we have their acetate group, which is the ester linkage with the CH2 group. Alright, so this is not quite done. So they actually do another step, which is kind of cool. Alright, so what's the next step? And I already gave you a hint. It's something about kind of diversifying or changing this part. And all they do is they basically react with another heterocycle. So nitrogen, nitrogen, sulfur, something like this, and oh, did I screw it up? Yeah, I screwed it up. Let's just fix it. Alright, just zoom in there. Let's change this around a bit. It's actually single bond there. Nitrogen, nitrogen, double bond. Alright, cool. Got that. And SH. And they use a base, and what's going to happen is pretty cool. The base just takes off the proton. I'm abbreviating. It's a two-step process. So yeah, first the base takes the proton, then it makes an S minus, right? So it goes onto the sulfur. I just don't have space to draw that. But essentially, you make a S minus, and those are super good nucleophiles. And essentially, after as a second step, it attacks there. It kicks acetate as a leaving group, which is weird because acetate's not the most common leaving group. With good enough nucleophile, it's reasonable that it might leave, but we usually don't use acetate as a leaving group. It's probably though because sulfur is such a good nucleophile. Okay, so what's our final drug look like? And what's the mechanism when this attacks and kicks off a leaving group? It's 2 numbers and a letter. SN2. Right, base takes the proton, makes a nice S minus, and then the S minus does the attack, kicks that off. Alright, so the final drug then, cefazolin, let's give ourselves some space. It's going to look kind of like the top, but then with this thing attached to it. Tetrazole. Oh, wrong. It's got the nitrogen right there, and a carbon there. Alright, good. Yeah, so 4 nitrogens. 1, 2, 3, 4, and this nitrogen's attached. And then you got your 4-member ring. To draw it kind of small because I screwed up and didn't give myself enough room. Shorten the arrow a bit. There you go. Alright, so yeah, let's draw this nicely. Okay, cool. So now we have a CH2, right? CH2. And what's connected to the CH2? The sulfur of this thing. Sulfur. Nitrogen, nitrogen. Oops. Double bond. Cool. Yeah, that's the final drug. Alright? So it's simply attachment of those things. And this is called cefazolin. What else? Let's see. Just for fun, let's think about naming this thing. This heterocycle. Any ideas how you name it? And we call this a tetrazole because there's 4 nitrogens. This is something-zole. It's got 2 nitrogens in it and a sulfur, which is often called thia or thio, I guess. So the name of this is basically something diazole. Diazole for 2 nitrogens. So it's called thiodiazole. Thiodiazole. So heterocycles have a fun naming system, and you see them in all sorts of drugs. Thiodiazole. Okay, that is a thiodiazole. Okay, cool. So what about cephalosporin? I think it's kind of cool that you have 2 points of variation. So you could kind of change this part, you could change that part. I'm sure they did that many times to kind of find the optimal thing on the left and the optimal thing on the right. What else? And then also, yeah, it gives them kind of more space to explore. They can kind of explore this, and the chemical space, we call it, to explore this and that. Let's see. So this is a broad spectrum antibiotic, so it's active against both. Broad spectrum. It's used for a whole bunch of types of infections, respiratory tract, urinary tract, skin infections, blood infections, all sorts of things like that. And it's just, it likes to kill bacteria, gram-positive and gram-negative. Okay, cool. Alright, so we got through that one. Alright, so let's talk about the mechanism of it. So we're kind of done with the synthesis of these things. How do they disrupt bacterial, well, basically kill bacteria? They are bacteriocidal, I guess. They actually kill bacteria. You have a really cool mechanism of action. I have a cartoon figure also, but let's start with just kind of a hand-drawn little figure. Alright, so we have penicillins and cephalosporins. So they basically do the same thing. The big difference is that cephalosporins are able to kind of sneak through gram-negative bacteria cell walls a little better, although at least ampicillin is able to do that too, of the penicillin series. Basically what they do is they inhibit something called DD transpeptidase. DD transpeptidase, which is a bacterial enzyme. We'll explain what it does in a second. Alright. And it's also on my cartoon figure. Okay, so in a nutshell, it's involved in the synthesis of the peptidoglycan, which is that little. I don't want to call it the cell wall because it's kind of maybe the cell wall in the gram-positive, but the inner cell wall in the gram-negative. It's like a matrix of sugars and amino acids that are kind of cross-linked. And the enzyme assists in this cross-linking effort. We'll see what that is in a second. All right. So amino acid cross-linking. We'll just say that. Amino acid cross-linking. That's a good summary of it. and it builds this matrix, like a impermeable matrix. That's at least the goal of the bacteria. Okay, so that's what it does. That's what these do. And of course, the beta-lactams roughly look like nitrogen. Something like this, blah blah blah, right? Okay, so that's pretty pretty lethal to a bacteria. It's lethal to a bacteria because if your drug destroys its little surrounding environment, the peptidoglycan, then the bacteria is dead. So bacteria kind of evolved to become resistant to these drugs, and there's an enzyme, a bacterial enzyme. This is one bacterial enzyme. Another bacterial enzyme called beta-lactamase. Beta-lactamase, which is another bacterial enzyme that evolved to kind of destroy penicillins and cephalosporins. It's another enzyme. And what it does, this just kind of shows the idea, is that serine 70 on bacterial beta-lactamase, serine number 70, serine of course is the amino acid with a primary alcohol, essentially destroys these. So serine 70, and it inhibits it basically, but ultimately it destroys. You know, we're using our drug to block and inhibit DD transpeptidase, then the bacteria is fighting back and it's blocking our drug with beta-lactamase. And essentially it's pretty cool, I guess. Serine just attacks and kind of electrons go up, electrons go down, and then break this off. And beta-lactamase, what do you think that stands for? Well, ACE usually hydrolyzes things. This is basically hydrolyzing the drug and destroying it, because the beta-lactam is kind of important in the activity. Okay, so when that happens, what this does is it cleaves the beta-lactams and destroys them. And that's really horrible. If you're trying to treat a bacterial infection, right? You're doing one thing, and then the bacteria is doing something else as a kind of drug resistance mechanism. Another name for this beta-lactamase is also, aka, it's called penicillinase. That's another name for it. Penicillinase. Okay. Yeah. So, what can we do to stop the bacteria from destroying our drug? Well, we can throw in a beta-lactamase inhibitor. So we can throw in our drug, a different drug, a second drug. In addition to our penicillin and cephalosporin, we can block this enzyme through a cool mechanism. And beta-lactamase inhibitor. And there's a couple of them. You could probably even Google beta-lactamase inhibitor and see some more of them. But one of the common ones is called clavulanic acid. C-L-A-V, lanic acid. Clavulanic acid. So it's actually a beta-lactam itself, but it's not the same kind of beta-lactam that we use as a like, you know, the way cephalosporins and penicillins work. But it is a beta-lactam, so it's the structure of clavulanic acid is actually a beta-lactam. It's a pretty simple molecule. The primary alcohol over here. So much simpler than like ampicillin or a cephalosporin. And a carboxylic acid here. That's clavulanic acid. And it basically inhibits beta-lactamase. Okay? And that kind of helps our penicillins and cephalosporins do their antibiotic goal. Okay? There's another one that's kind of popular, and it is called, we'll draw that one down here, another beta-lactamase inhibitor. It's called sulbactam. And it's another beta-lactam. It's got a weird functional group up top. Two methyls, double bond O, and the same carboxylic acid. Sulbactam. All right. And let's see what else about this. Do you know the name of the functional group? The weird functional group there. What's that functional group called? S double bond O. Do you know that one? Just learning new weird functional group names. It's not a sulfoxide. A sulfoxide is that, right? S double bond O. Maybe we told you about this. Yeah, sulfoxide's double bond O. But what if you have two double bond O's? It's not a sulfoxide, it's a sulfone. S-U-L-F-O-N-E. Sulfone. Okay. That's a sulfone is a higher oxidation state. Functional group is sulfur. S double bond O, double bond O. I think we also mentioned other sulfur functional group, like if you have a nitrogen, what's that called? It looks kind of like an amide, but it was sulfur. That's not a sulfone. That's a sulfur. Sulfone almost looks like a ketone, right? But it's sulfur, and you have a high oxidation state. This is not a sulfone. It looks kind of like a sulfone, but it's what? It's called a sulfonamide. I think these were like the sulfa drugs we talked about earlier. They have a sulfonamide functional group. Okay, maybe, let's see, what else do I want to say here? Oh yeah, so you might think, now that we have this kind of cool strategy to inhibit beta-lactamase, which bacteria is used to inhibit our drugs, couldn't we just like co-administer like a penicillin and a beta-lactamase inhibitor at the same time, or a cephalosporin and a beta-lactamase inhibitor, like clavulanic acid or sulbactam? And the answer is yes, you can totally do that, and they actually have commercially available cocktails. So I'll just write those down here. Can co-administer a beta-lactam antibiotic, which could be a cephalosporin or a penicillin, and a beta-lactamase inhibitor. And a couple of the formulations, clavulanic acid, plus amoxicillin, which I think is a penicillin derivative, mostly from the name. I don't have the structure in front of me. That is equal to something called augmentin. Okay. And then ampicillin, or we'll say sulbactam, which is the other one, the sulfone one. Sulbactam plus ampicillin is equal to something called unison. as a drug. And it's a combination of penicillin, one of the penicillin derivatives, and sulbactam, beta-lactamase inhibitor. So anyway, that's pretty cool. All right. Okay, I have a really cool cartoon figure that talks about mostly what's going on with the DD transpeptidase and how what it actually does. I'm probably just going to present that in our next synchronous lecture, and so you guys can ask some cool questions about it, or if you know, it's pretty cool, and I thought I'd just present it next time. So I think we're good. Hopefully this gave you a little bit of a feeling of how penicillins and cephalosporins work, how this nasty enzyme, beta-lactamase, kind of destroys drugs that we use, and it's really for self-survival of the bacteria, because it doesn't like to be killed by our drugs, and then how we can kind of counterattack with the beta-lactamase inhibitor, which I think it's a pretty cool approach. And you know, it's kind of like a continuous struggle on creating antibiotics that work, because more and more bacteria are evading our antibiotics. And there's a lot of other next generation, or like we'll say last line antibiotics that are used for drug-resistant bacteria, like vancomycin, I think. And also the other drug targets, so DNA gyrase, and you know, that it helps having some different tools in our toolkit. Okay, so I'm going to stop now. I'll do the little cartoon diagram next time, and then we'll also talk about an interesting other little tidbit, how the beta-lactamase inhibitors work. They actually, it's called a suicide substrate, and basically what that means is you know, I'll show you, but essentially the serine will permanently, it'll do the same thing, it'll attack these guys, but in a way that this permanently gets attached, and then this gets deactivated. So that's a really cool story also. So we'll talk a little bit about that, and how these are called suicide substrates. Okay, so I'll talk to you guys soon.